Hi, welcome to BC Video 11.2/11.3 Part 1, Parallel Vectors and Dot Product. Introduces three-dimensional vectors. We are not going to do three-dimensional vectors. However, embedded in these sections are things you do need to know about two-dimensional vectors. So the only thing in 11.2 is the definition of parallel vectors. Two non-zero vectors u and v are parallel if there is some scalar c such that u equals c times v. So if you think about it, if they're parallel and you put them both in standard position, they would sit on top of each other if they were pointing in the same direction. So for example, if this was v, then 3 times v would be this red vector. So these are considered to be parallel because you could actually simply translate them around. Okay, if they were opposites of each other, then what will happen is they'll be parallel again because one of them is a scalar multiple of the other. For example, if this was u and v was negative 1/2 of u, then v would look like this. So if they give you two vectors and they ask you are they parallel, you just need to check that one of the vectors is indeed a scalar multiple of the other vector. Now you could put this in either order. So you do distribute the scalar, and of course the two vectors are equal only if their x components are equal and their y components are equal. What has to happen when you solve for c is you must get the same value for c. 11.3, you need to know two things, the dot product and the angle between the vectors. So the dot product, and I'll explain where it comes from in a second. Also called the inner product or the scalar product. It is a operation performed on two vectors. They don't show it as a big enough dot. It's actually a very large dot. And now they use u1, u2 as the components and v1, v2. I prefer to use x's and y's. I think that's easier for you to use, x's and y's. So the way I'm going to look at it is the dot product is the product of the x components plus the product of the y components. Now, the components themselves are scalars, so the dot product of two vectors does not give another vector. It gives a scalar. It gives a real number. Unlike if you add two vectors or subtract them, you will get another vector. So for example, if you had the dot product of these two vectors, it's equal to the product of the x components plus the product of the y components. Now where does this come from? What's the source of this? If you were to draw two vectors purposely perpendicular to one another, the components of vector u are x1, y1, the components of vector v are x2, y2. Since the vectors are perpendicular to each other, then the slope of vector u would have to be -1 over the slope of vector v, negative reciprocals. Well, the slope, of course, of vector u is rise over run, which is y1 over x1, and the slope of vector v is y2 over x2. So if you substitute that in, simplify the right side, do a cross product, and bring it all over to one side, you find out that if the product of the x components plus the product of the y components happens to equal 0, then that would mean that the two vectors are perpendicular. So that's where the dot product comes from. That's why they invented this thing called the dot product. Now, in vectors, just like a constant is called a scalar, and the sum of two vectors is called the resultant vector, and the length of the vector is called the magnitude. Vector algebra has its own terminology, its own vocabulary. So instead of perpendicular, they define the vectors to be orthogonal, but it really just means perpendicular. So you have a theorem or a definition of orthogonal vectors, which is that two vectors are orthogonal, which is perpendicular, if and only if the dot product of those two vectors is 0. Now there are some properties about the dot product. You can see that you can change the order. The dot product is a commutative operation. Also the distributive property. U dot product of v plus w, you can distribute that dot product through. Same thing with a scalar times a dot product, you can distribute, you will not distribute that through. C times the dot product of u and v is either C times u dot product with v or u times C dot product with v. Now honestly, all I would do honestly is just find the dot product of u and v and then multiply that scalar by C. The zero vector dot product with any vector is going to give the scalar 0, because you'll have 0 times the x component plus 0 times the y component of v, and you will get a scalar. Now this last property is going to come in handy when we actually see the proof of the formula for the angle between two vectors. And that is, if you take the dot product of a vector with itself, you know you're going to get a scalar. Well, it turns out that that's the same thing as the square of the magnitude of that vector. So first of all, here's the one where you have the zero vector dot product with any vector gives the scalar 0. And here's this other one we were just talking about. If you actually did both sides independently, you did the dot product of a vector with itself, and on the other side you squared the magnitude of the vector, you'd see that you get the same thing.